let's first recap what we learned last week. Last week we discussed a brief introduction of a modulation. Okay, and remember that the modulation is to load your message into the carrier, right? So you have your message. We call that the information-bearing signal, and this message, this signal is what you want to transmit. Okay, what you want to deliver to the receiver. And how to do that is you are using carrier wave, okay, which we call as a CT. And this message signal is empty, okay, in our context. So in a modulation, in continuous wave modulation, we have two different things, right? Amplitude modulation and frequency modulation. And we are right now talking about amplitude modulation. Okay. In amplitude modulation, we have four different things. And this is a basic amplitude modulation, which we talk about today. And later, maybe next week, we talk about double sideband, DSB, and later SSB. Okay? And you need to see the differences. Okay? What the difference and what is the pros and cons for each of the signals, each of the modulation. And here's a basic of modulation, amplitude modulation. We have a carrier signal like this. And you see that this is a simple sinusoidal signal. Okay? Remember that we discussed why we are using sinusoidal signal as a carrier, right? So this kind of sinusoidal signal, cosine with a single frequency, is the effective way of delivering effective carrier for in our medium, right? Wireless wireless medium. So we are using this one as a carrier, and carrier has its own amplitude, and carrier has its own frequency. This is a single frequency, just a pure cosine, right? Single frequency. We call that as a carrier signal. We have a message, MT. Okay, MT is a message signal. And now, in order to put this MT message into the carrier, how to do that is you can put this message into the amplitude part. That's what we call as amplitude modulation. Or later, when we put this message signal into the frequency part, that's going to be frequency modulation. So right now we are talking about amplitude modulation. So put this message into the amplitude part this way. Okay? So put this message into the amplitude. So previously the carrier has its own amplitude AC, but now when you put the message together, now AC 1 plus Ka MT, this is going to be the amplitude of your carrier, right? So that's how you combine the message with the carrier. Once you do that, this is what happened in the signal. So this one visualize what happened. This is a MT, original message MT, and we multiply the Ka. So somehow this Ka will amplify, make it a little bit bigger or smaller, depending on the Ka. Typically, we use Ka a little bit smaller than 1. Okay, so make it a little bit smaller, and then you are adding DC component, which is just 1. And the reason that you are adding plus 1 is because you want to lift this signal up like this, so you don't have no negative signal. Okay, so that's the main reason. You want to make it positive, everything positive. In order to make everything positive, that's why you are multiplying Ka, right? Because if you have a negative part, and let's say this is minus 2. If this amplitude is minus 2, then you are adding plus 1, still it's minus 1. So that's why you're multiplying, let's say, 1 over 2, so that this minus 2, original minus 2 becomes minus 1 when you multiply 1 over 2, right? And then plus 1, then it becomes 0. So you are making smaller a little bit and lift that up by adding plus 1. Now we see that the signal is going to be always positive over the time domain. Now it's time to multiply the carrier. And carrier is the same carrier that we are using here. And remember, this carrier has its own carrier frequency, and this frequency is very fast. Much, much faster than the frequency in the message, right? much faster. It's pretty fast signal. So very high frequency compared to your message. When you multiply this one with this, now you're going to get this one. Okay? So this blue signal still is like a sinusoidal signal, but the envelope now changes. So this is what you transmit over the air through the antenna. That's what we call as ST. Okay? ST is what we transmit eventually. This picture shows you what happens if we do not add the DC component. Okay? If you do not add a DC component, then you are not lift this up. So this negative part is still there. Okay? Once you have a negative part, what happens is when you multiply this cosine into negative part, now then this part becomes minus cosine because this one has a minus. So here's a positive, this is negative. So when you multiply this one into here it's a cosine, but this part is minus cosine, again cosine, plus cosine. So therefore you see this kind of picture, and right here you see the phase reversal. What that means is the phase is going to be positive, negative. It's being reversed, right? Right? Positive plus 1 and minus 1, it's a phase reverse, right? If you say the positive plus 1 is phase 0, minus 1 is going to be phase 180 degree, right? Minus 5. So it's same as a phase reversal. So you see the phase is reversed right here. And what's the problem of phase reversal? The problem is that we cannot use envelope detector. That's the problem. Okay, I'll tell you the details, what that means today, a little bit later. But the main reason is that we want to use envelope detector. Okay, envelope detector is part of the receiver. Right now, all of these things is a transmitter. Okay, we are talking about transmitter right now. So when you transmit, you do these things and make this signal and transmit. Eventually, this signal is received, right? Received by the receiver. And in the receiver, you need to do something in order to recover from here to there, right? Eventually, we want to recover this one from this. So you need to go back, right? That's what you do at the receiver. And the easiest way to do it at the receiver is to use the envelope detector. So this is what you do at the receiver. So but this is a simplest receiver, very simple. That's why we want to use this receiver, because this is very simple. But if you have this kind of signal, and if you transmit it with the phase reversal, you cannot use the phase detector at the receiver. So that's why. Okay. And this is the condition that you need to meet in order to use envelope detector. Okay. So that basically means is that you multiply Ka, right? Here, you Ka, and empty, then should be the less than 1. That means your negative part should be at least minus 1. If the negative part is lower than minus 1, then you add plus 1, still it's going to be negative. So that's a problem. Okay, so that's a condition. Okay, once you do this, right? Let's take a look at this. This is the ST. In the previous slide, we see that this was a cosine carrier, and we have a message MT, and we first multiply Ka into the MT, and we did plus 1, right? So this is the signal we transmit over the air, right? Let's go back this one here, this one, right? Remember that right here we have MT. First, you multiply Ka in the MT. So right here, it's going to be Ka times MT. Now you do a plus 1. So right here, what do you have? Right here, you have 1 plus Ka MT, right? And now you multiply this. So you're going to get this one right here at ST. So this one, let's move to here. This is this one. Since we have two terms, right? We have two terms. So let's expand that. Then you multiply cosine into here. Then we get an AC cosine, like that. On the second term, we have AC KAMT cosine, which is this one. Right? We have two terms. We have two different terms. Still, we are talking about this signal in the time domain. And what you want to look at is what does signal look like in the frequency domain. Okay, that's what you want to look at. So in order to see the frequency domain, what we do is we do Fourier transform of this signal. Okay, Fourier transform. Then you see that the cosine, when you take a Fourier transform, it becomes like this, right? It's like you have a FC, so it's going to be like FC impulse here, and another impulse in minus FC. It's like this, right, in the cosine. And each impulse has the amplitude AC. So this part, AC cosine, since this is a pure cosine, you have this one. AC over AC divided by 2, delta, and another delta. And this one has the frequency FC. This one is a minus FC, right? This is just a pure cosine in the frequency domain. Right here, this second term, again, we take the Fourier transform. But this one actually is the ACKA. This is just simple constant. And MT times cosine. Okay, MT times cosine. Now when you take the Fourier transform of this, since we have a cosine multiplied into MT, now we are going to get these things. These things. Why is that? Okay. Let's say we have MT in time domain. Okay? And take a Fourier transform. Let's suppose that we get a MF. This is a frequency domain. This is time domain. These two are like a partner, like a pair when you take the Fourier transform, right? Fourier transform, inverse Fourier transform. Okay? Now let's say you multiply the cosine here. Then what happened in here, in the frequency domain? That's what happened. This is what happened. How do you know? That's what we do in the last week, right? Remember that we discussed Fourier transform property, many properties, right? We reviewed many properties. This is a modulation property, property 12 or something like that, right? So that's why we reviewed all these things last week. So if you are not comfortable about this, then go back to the last week lecture note and take a look at the property, modulation property. When you multiply cosine, now then this MF becomes this one. Okay? This becomes this. That's a modulation property, right? Now let's understand what this means. Let's say now our MT in time domain, let's say it looks like this. Just the example. That's MT. When you take a Fourier transform of this, in the frequency domain, this is time domain. Let's say in the frequency domain, let's say we are getting this one. Just the example. Okay? Just the example. Suppose this is the case. Okay? Let's say MT looks like this. And when you take a Fourier transform of that, let's say we get this one as an example. In that case, what happens when you multiply cosine carrier into here? Okay? Typically, the carrier frequency is very fast, very high frequency. When you multiply this into here, now what happens is you're going to get something like this. Okay? You still have the envelope, but in the envelope, inside envelope, you have the very fast sinusoidal signal multiplied into this MT. So this is what you have in time domain. When you multiply cosine, this is what you see. Okay? So this is now changed to this one by multiplying cosine. Then what happened here in the frequency domain? This now is changed into like this. Okay? Like that. So when you multiply cosine into the time domain signal, in time domain, this one will be changed into this one. When you look at the same thing in the frequency domain, this one was the original frequency response of your signal. Now this one becomes this way. So originally, you have all of your frequency in the baseband. This is called the baseband because we have all the frequency around the 0. That's a baseband. Okay? And now, by modulation or by multiplying cosine Fc, what happens is now this becomes this way. Okay? Now the center frequency is not 0. It actually moves, shifted into Fc. So this is like a frequency shifting or modulation. Remember that we discussed that last week? So that was now center frequency moved to Fc and also minus Fc. The one thing that you need to be careful is that here, maybe the amplitude is 1, but now here the amplitude is going to be 1 over 2 because there is another 1 over 2. And you need to have the same energy, right? So the original energy is now become half. Half goes here, the other half goes there. Okay? So the in power, the power is divided by 2. So it go there, go there. But eventually, when you do the modulation, this is what happened in the time domain, and that's exactly what happened in the frequency domain. So this is what we call as modulation. Okay. So simply speaking, then what is this one? This is a carrier frequency, right? So why do you move this frequency signal into here? Why is that? First reason, this is your message. We want to load this message into the carrier because this electromagnetic wave or sinusoidal wave is an effective way to transmit. So we want to use this electromagnetic wave. Okay? You want to put this message into the carrier. Once you do that, now the energy moves to Fc. And remember that, let's say, every one of you using cell phone, right? What's the carrier frequency of your cell phone? Does anyone know? What's your carrier frequency? Huh? Everyone probably heard about the carrier frequency of your cell phone. You can even read it in the newspaper. 2.4 gigahertz, something, 1.8 gigahertz, or the old cell phone use a 900 megahertz, or 1.8 gigahertz. You heard about something like that, right? 1.8 gigahertz, something like that. What is that one? So the newspaper says these days our cell phone network is using 1.8 gigahertz. What does that mean? This is 1.8 gigahertz. 1.8 gigahertz in your cell phone. Let's say in Wi-Fi, we are using Wi-Fi all the time, right? Wi-Fi. What's the frequency that Wi-Fi is using? 2.4 gigahertz. This is the 2.4 gigahertz for Wi-Fi signal. Okay? So we have actual frequency, and each system is using different carrier frequency. Wi-Fi is using 2.4 gigahertz band. Your cell phone is using 1.8 gigahertz band. Right? GPS is using another band. Military, they use another band. Right? Each of the frequencies is used for other purposes. If you use same frequency with another system, then there will be collision. Right? let's say you're using cell phone 1.8 gigahertz, Wi-Fi using again 1.8, then both systems it's not going to work because they collide. So each system will use a different frequency. Okay? That's regulated by the government. So that's a FCC. That's FCC. Okay? So this is called the carrier frequency, and this is what we call as a bandwidth, and that's the band, frequency band that is assigned or that is given to you by the government or some organization. Okay? So you are permitted to use this one for your communication. So typically this is given to you. FC you cannot select. This is given to you. Okay? So 1.8 gigahertz is for your cell phone, 2.4 is your Wi-Fi. So that's a frequency. So therefore you are not using this one. You cannot use this one, right? You cannot use this one. You cannot use these frequency. You're going to use your own frequency. Like a cell phone, 1.8, for example. Okay? So that's why you're going to load your energy into this area, this frequency area for your signal. So that's what happened in the frequency domain. So therefore, when you see this, right, you want, again, the same way, you have your own MT, multiply the cosine, then we see that this is what happened in the modulation. So in the frequency domain, we are going to see this one. So we have two terms in ST. For each term, we do Fourier transform. Now we see that this one, and from this second term, we get this one. When you see this, right, we have four terms. We have two impulse, direct delta, and two of these things. We have four terms. So let's plot this in frequency domain. Now we have this one. The left picture here is just an example of MF. Okay, just an example. Like in my picture here, this was MF. This was MF. But in here, as an example, let's say this is MF. Okay, just an example. In that case, now based on this modulation, this one was originally in the baseband. Now this one is shifted in the frequency. So now the center frequency becomes FC and minus FC, as I said here. Okay. Plus, you have two direct delta function, and each one is like in FC and minus FC. So now we have one direct delta here, which is in FC, another delta here, minus FC. So this term goes here as delta. And this one now appears here as a delta. This term, MF plus FC, is this triangle. And this is this triangle. So we have four terms, and we have four pictures, four of them, right? So this is the whole picture of this signal in frequency domain. Okay? Or when I draw this one in here, what happened is, if this is MT, now we get an MF like this. And when you do this, we have like this. So you have your own MF plus you have direct delta. And why do we have this direct delta function? Because we have this term. Okay, this direct delta comes from this, right? Right? Because this one, you take a Fourier transform, you get this. And this is the delta, right? So this direct delta comes from this. And what is this one? This is originally this one, plus 1. So this one, we have this term because we added DC. Right? In the previous slide, remember that we added DC, plus 1, right? Because we did a plus 1, now we have this, and because of that, in the frequency, now we have this direct delta. Okay? And again, what was the reason we are adding plus 1? In order to use envelope detector. Okay? We're going to talk about that later. So we have this one. this slide basically give you a little bit simple example. Let's say our message in the previous picture, right? We didn't assume anything. Empty is just still empty. Okay, we didn't use specific empty, just general empty. But now, as an example, let's suppose that our empty, our message signal is just simple sinusoidal signal. Maybe in this case, I think that you may be confused because we are seeing many different sinusoidal signal. But this is just simple example. This is about message, not the carrier. Okay, we still have a carrier here. We just see that the simplest example of our message, this is our message. And our message, as an example, let's say is this one. Okay, it's just a sinusoidal signal. And since this is a cosine signal, this one has its own frequency, FM, message, FM, and amplitude AM. And originally we have 1 plus Ka MT, right? So instead of MT, we are going to use this one. Put it here. So now we get this one as ST. Now let's look at FM here and FC. So since we have two different cosine, and each one has its own frequency, which one is much higher? FC is a much higher frequency because this is a carrier. And FM, maybe it's very slow. That's message, right? Again, just the example. Okay. Now when you put this, you probably want to look at this part, KA-AM. Okay, KA-AM. This is just constant value, just constant. But we group these together, KA-AM, multiplying these two constant, make it group, and we want to replace this into mu. Okay, so mu here is same, mu equals to Ka times AM. Okay, we want to replace this into mu. Why? Because we want like this, right? Like this. Why? Because we want to call this one as modulation factor or percentage modulation. Okay? So we want to put some meaning into this constant mu. So mu has certain meaning right here. Okay? So let's put this one as a mu. When you look at this mu, right? What was Ka? Ka was the gain in order to reduce your original MT. Remember? Remember the Ka?
Yes.
Okay. And what was the AM? AM is the amplitude of your original message. Maybe your original message can be big or your original message can be small, right? So depending on how big your original message is, AM is the amplitude of your original message, and Ka is the gain that is multiplied into your message, right? So the mu is modulation factor. And see here, to avoid signal distortion, this mu, modulation factor, must be below unity, must be less than 1. That was actually what I said here, right, in the earlier. So that is actually kind of the modulation factor. When you multiply Ka with the message amplitude, that should be less than 1. Okay, I'll tell you why that's the case. Let's look at here. Let's say this is our message, the previous message here, this one. Okay, we are still looking at this example. Our example is that our message is simply a cosine. And let's take a look at this cosine message that looks like this. This is a simple cosine, right? Simple cosine. And that's our message. Since our message is a pure cosine, when you take a Fourier transform, it looks like this, right? You take a Fourier transform cosine, it's like this, right? And the center frequency here, the frequency component is FM minus FM, because this is cosine 2 pi FM t, right? So we have cosine. So this is just simply speaking, this is just cosine in time domain. This is cosine in frequency domain. But in our example, in our message, the cosine, this cosine, has the frequency FM. So just, nothing difficult, just cosine. In time, in frequency. This one, B, is the carrier. This one was a message. And the second, this C, B, is a carrier. Carrier is again cosine. But this one has the carrier frequency FC. So this is much faster. And again, this is cosine. So therefore, when you look at this cosine in the frequency domain, again, you're going to look at this. But only the carrier frequency is different. So difference between this message here and carrier here is that both of them are cosine right now, but the frequency is different. This one is much lower frequency, so it goes slow, and the carrier frequency is much faster. Okay, it's the carrier frequency is much higher, FC. So that's the difference. Okay. Now using these two, what you want to do is that we want to do this. Okay, we want to create ST. Okay, we want to create ST like this. So put this message here, right here, because this is MT. And Ka, you multiply Ka into MT and plus 1 and multiply the carrier like this. Okay, like this. Once you do that, now you see this picture. This picture. How do you get this picture? How to do that is you are multiplying Ka into this MT. So when you do that, then maybe this MT becomes a little bit smaller. Still sinusoidal, but maybe the amplitude is getting a little bit smaller. Now do a plus 1, then this is lifted up, right? Now the cosine goes up like here. And then you multiply this carrier into that. Then you're going to get this. This one right here, we call this envelope. This envelope is same as this one. So now we lift this up so that this one goes up like here. And then you multiply this cosine carrier. That's what happened. So this is ST. That's what you transmit over there. When you look at this ST from the frequency domain, this is what you see in the frequency domain. And when you compare this, what you can see is that here we have FM minus FM. Now, by doing modulation, by multiplying cosine like this, what happened in the frequency domain now is to change it like this, right? The energy is divided into positive and negative. Same thing. Here in the energy, this is the original message. Now this one is divided into positive and negative. Now you see these two, and also these two, right? So this one, we have a frequency difference. This is 2 FM. What's the distance between these two? 2 FM, because this is FM minus FM, 2 FM. These two are 2 FM, this. So this is divided into positive. Half of the energy goes to here, becomes these two. The other half of the energy goes there, becomes these two. Okay, like divided. In addition to that, we have this direct delta here in the middle, right? This blue one. That is this one in the middle. So this picture actually is same as this one. Exactly same. The only difference is that this is the case when we use this MT. Okay, this MT. And this is the case where you use this MT. That's the only difference. MT can be anything because that's your message. You can transmit any message you want, right? Sometimes that kind of message, sometimes this message, any message is fine. So what is important is that this message or this message can be anything. Okay? In frequency domain, this can be maybe triangle, this can be rectangle, anything. But important thing is whatever shape we have in the frequency domain, the half of the energy goes here, the other half goes there. Okay? And in addition to that, we are going to always have this impulse for each side. So eventually it looks like this. So we are talking about same thing exactly. Okay? This one, same. This one is a simple example actually, because our message is simple. This is a more generic picture, but both are basically same. Yeah. Okay, so what we want to talk about here is let's take a look at here. So as I said earlier, this is the original picture, original signal in the frequency domain. When you look at this original signal in the frequency domain, we don't have any impulse, right? This one is not impulse. Maybe you are confused. This is not impulse, right? That is just axis. So there's no impulse here. Because this is just purely the frequency response of your message. We don't have any impulse. It just looks like this. When you do the modulation, especially in our amplitude modulation, now in the pass, this is called the pass band. In here in the pass band, we have now the impulse, right? The Dirac delta function. What that means is you have original energy, this much of energy. Now this energy is divided into positive and negative. In addition to that, now you have additional arrow here, right? Additional Dirac delta. And this Dirac delta, of course, will have energy, some energy. But this Dirac delta is purely a carrier part because we added DC, right? So because of the DC, we have this one. Okay? So what that means is original energy you have goes to this white one and also into the blue Dirac delta. So Dirac delta, blue Dirac delta is somehow is a waste because your energy, your signal is only in here. This one does not have your energy, does not have your signal. This one only has energy. Okay? And the reason that we are looking at this modulation factor is because when you change this modulation factor, now the size of this Dirac delta compared to your bandwidth now it changes. Okay? Depending on this modulation factor, depending on this value, sometimes so we are looking at three different pictures here. Three different pictures looks almost the same, except that this one has a much bigger Dirac delta. This one has a much smaller Dirac delta. Okay, so that's the only difference. Now, depending on this mu value, depending on this modulation factor, sometimes you get this picture, sometimes you get this, sometimes you get this one. So which one is better? In some sense, this is the better. This is the the best one. Why? Because we have a limited energy. We have only this energy. And this energy, this limited energy will go to this white one and also into blue one. And blue one is waste. So you are wasting a lot of energy in this case. In this case, you are wasting only small energy. And most of the energy goes to this white part. And white part is what we need because your information goes into white. Okay? Blue, you don't have any information. Blue one, no information, just energy. So you are wasting a lot of energy in this case. In this case, you are wasting just small part energy. So somehow in that sense, the blue one is bad, right? Blue one is a bad guy. Why? Because this blue one has no information, but it consumes a lot of energy. Then why do we do this? The reason is, okay, why do we have this blue? In the previously, why do we have this blue? That's because we added DC. Okay? Then why did we add the DC? Because we want to design a simple receiver. We want to do envelope detection in the simple way at the receiver. So that's why we are adding blue. But blue is actually waste. Okay? Completely waste. So this picture here is telling you how much energy is splitted. In this picture, we have two curves. One curve shows carrier. The other curve shows sidebands. Okay? This part, okay, this curve shows you the power of the carrier. Carrier in this case means that blue one, blue guy. Okay, the direct delta. And this one shows you the energy, okay, energy included in the white part. Now it changes, right? And what is the x-axis? This one is a percentage modulation. That's a modulation factor, which is this one. That's what we are seeing on the x-axis. Okay? So what we are trying to do is we want to change this one. Okay? We want to try different value of this one and see what happens. Let's see. If the mu is 0, this is a percentage, so that means 0. 100 means it's 100%, meaning 1, right? So this is 0. If mu is 0, then let's see what happens. Let's go back here. Let's say mu is 0. Okay? This is 0. Then what happened? We don't have any this one. We only have a carrier. And this carrier actually is just cosine, so therefore we only have this one. Only have this one, middle one, right? So 100% energy goes to middle one, which is the carrier, right? So we have 100% of power in the carrier. Your information has 0 energy because mu is 0, right? Now let's increase the mu, and let's say mu is like 50%, 0.5, 50%. In that case, your carrier power is a little bit smaller and smaller, and the energy in your sideband, what is a sideband? This one is a sideband, the white one. White one is a sideband. The energy included in your sideband is increasing a little bit. So as an example, if modulation factor is 0.5, this is what happened. Your side lobe, sideband, maybe has 20% of power. Still the 80%, most of the power is in the carrier. So that's kind of picture like this. Actually, this is, let me draw a little bit different way. So it's maybe like this, like this. So that's the case of mu equals to something like this, right? The blue one, carrier, pure carrier, we call this pure carrier. So again, remember the carrier? Carrier is something that you created when you transmit, and at the receiver, you are discarding the carrier, right? So carrier does not deliver any information. Carrier is just to use, to deliver. Your information is included in the sideband. The carrier, blue one, has no information of your message. But that one has the 80% of the energy. The white one has only 20% of the energy. Okay? So that's what happened when the modulation factor is 0.5. So 80% of the energy is completely waste. That's not good, right? Now let's keep increasing. When the mu is 100%, now then carrier power is still decreased, and your sideband power energy is going up, right? So somehow in that case it's like 50, 70%, 60% and 40%, something like that. So then in that case it's like this. Okay, something like this. So this equation shows you how to calculate this this carrier power and this frequency power and things like that. But we can come back to this later. Let's take a look at this. When the percentage modulation or modulation factor is less than 20%, here, less than 20%, then in here, the power in the sideband, is less than 1%. So 99% of your energy goes into carrier. So it's really 99% of your waste. 99% of your energy is waste. This one shows you an example. Okay? So let's say, as an example, we choose the carrier amplitude AC is 1. This is carrier amplitude. And as an example, let's say carrier frequency is 0.4 hertz. And your message, again, we are still assuming a sinusoidal message, simple message. Now let's say message frequency is 0.05 hertz. And we want to look at three different modulation factor. Mu is 0.5, first case. Second case, mu equal 1. Third case, mu equal 2. Okay? Mu equal to 0.5, this is the case we call as under modulation. 1, 100% modulation, and 2, or higher than 1, we call this an over modulation. And I'll tell you what that means in the next slide as a picture. So let's take a look at each case. We have 3 different cases, right? So let's take a look at these cases in here. This is the first case. This picture shows you the first case. Mu equal to 0.5. When mu equal to 0.5, okay, with mu equal to 0.5, this is what's going to happen, right? Mu equal to 0.5. So remember that when you compare the power in the carrier and power in the sideband, this is about mu equal to 0.5, mu equal to half, right? Somewhere here. So we still see that the carrier has a lot of power, and your sideband has some 20% or some less power. So that's what you see here. And what you see here is actually this one. This is the whole picture of frequency domain. And when you look at here, okay, when you zoom in here, this is what you see. Okay. Do you see that we have 3 of them here? 3 of them. When you look at this one closely, this is what you see, right? So we have the middle one, which is the blue, this one, and we have the other 2. That is your FM, original message, and this one has a very little power. The middle one has a really big power. Okay, that was the case of 0.5. And when you look at this in time domain, now what you see is that your original message looks like this in sine. Okay, because we use the sine FM. Okay, with the frequency FM, right? Your original message is sine, cosine in this case. So your original message looks like this. Now in time domain, you lift that up, and you see that all the message in time is now well above the 0. It's all time domain. So in this case, it's very easy to use envelope detection because you want to recover this signal. That's your message. Now let's look at the second picture. In this picture, this is the case where the mu equal to 1. Okay, mu equal to 1. Now you expect that mu equal when you increase the mu, for example, mu equal to 1, the picture should change from here to here. Maybe this is what you probably see. Now compared to the previous picture, now what you see is that the middle one, the carrier power is a little bit reduced, and your message power is a little bit increased. Right? When you look at this in time domain, you see that you still see the cosine, your message. But now your lowest part of your cosine with your signal now hit 0. Okay? Hit 0. That's why we call this 100%. 100%. So in the previous picture, let's compare this one in the previous picture. In the previous picture, the modulation factor was 0.5. So in that case, even the lowest one is still positive, right? Some maybe positive 0.3 or something, still in the positive. But in the next picture, in the case of mu equal to 1, now the lowest one hits 0. Okay? And you see that the energy here in the carrier is reduced and the message is a little bit increased. Now let's keep increasing when the mu is higher than 1. This power in the carrier is still reduced. It's even further reduced. And the energy in your message in the sideband is even higher now. So it's almost the same in the frequency domain. And when you look at that in time domain, now what you see is that in the earlier, when the mu equal to 0.5, it was up here. When the mu equal to 1, now it hits 0. And this is the case of mu equal to 2. Now it goes into negative. So you see the phase reversal here. You see the phase reversal. Okay, that's what you see here. Phase reversal, because the signal now goes down to negative. So when you see this phase reversal, now the problem happens. What's the problem? You cannot use envelope detection. So in this case, mu equal to 2. This is the case of mu equal to 2. When you use a mu equal to 2, or mu is higher than 1, okay? This is just an example of mu equal to 2. When the mu equal to 3, mu equal to 1.5, you still have the same problem. So when the mu is higher than 1, in time domain, you see the phase reversal. So now we have a problem in using envelope detector. We cannot use envelope detector. That's a problem. That's a bad thing. But what is a good thing in this case? The good thing is that your sideband has a lot of energy. You are wasting less energy. So that's a good thing. Okay? When the mu is high, modulation factor is high, you see that you are wasting less energy. So that's a good one, but you cannot use envelope detection. That's bad. Going back to this case, the first picture, this one is the case of mu equal to 0.5. And we call that under modulation, right? In under modulation case, what is a good thing? A good thing is that your original signal is much above the 0. So it's always positive, so you can use envelope detection. That's a good thing. What is a bad thing? Your side lobe has very low, your sideband has a very small energy. And you are wasting a lot of energy. So that's a bad thing. So that's why, what would be the best selection? Most likely, this one, 100% modulation would be good selection, right? If you choose very high mu over modulation, again, let me do it again. Mu equal to 2. In this case, it's over modulation. What was the problem? You cannot use envelope detector because you will see phase reversal in time domain. But good thing is, you're wasting less energy. What about in mu equal to 0.5? In under modulation case, the problem is you're wasting a lot of energy. Good thing is, you can use envelope detection. Okay? So there's always a problem in each case. Now think about mu equal to 1, the second case. In this case, you still waste some energy, but better than under modulation case. You can still use envelope detection because your signal, the lowest point, hits the 0, but not negative, right? So it's very close. It's almost very close, like a 0. So you can still use envelope detection. Therefore, we can say that mu equal to 1 would be probably the best selection for you. So now we want to discuss a little bit about the energy, the envelope detection. So this is the receiver side. Okay, receiver side. So far we talked about a transmission side, and now once you transmit, you need to receive it, right? So this is a receiver. In the receiver, we have many different receivers, many different. And this is the simplest receiver. And in this envelope detector, as it says, we want to detect the envelope because envelope is your information in AM, right? Your information is in the envelope. So you just simply we want to detect, that's good enough. Mathematically, this is your signal transmitted, and we have no noise in this case. We are not assuming noise, right? Whatever you transmit, you receive it exactly. So no noise, nothing, no error. So therefore, this is ST, transmit signal. That's also what you receive as RT. RT is a receive signal. ST, RT, same in our case. Okay? Because there's no noise, there's no error. This is what you receive. You have a message signal here. You have a carrier multiplied to it. Now by putting the envelope detection, it's actually filtering. When you do this filtering, we are going to remove this carrier part. And then we come back to this one. And but still we have the DC part because we added the DC at the transmitter. And later we remove the DC. Then we are going to get this message back. And let me tell you what happened in here, a little bit more detail in this slide. So let's say this is what you transmit. Now you should be somehow, you should feel comfortable about this signal, this kind of signal. Because when you look at this signal, what do you see? Your message signal must be this one. This is your message, right? You originally have this message. And now by multiplying Ka and lift that up by adding DC, now it goes up like here. And then multiply this fast cosine, which is carrier. So therefore you see this signal. This is what it transmits. And now you receive this, right? You receive this signal. And our goal at the receiver is to recover this. That's our goal, right? You're going to receive this. From here, from this, you want to recover this. And that's what we call as envelope. Envelope. So that's why we call this envelope detector. The easiest way to do it is to use this kind of circuit. That's a very simple circuit, right? You have only one capacitor, two resistors, and something like that. One, diode or whatever, something like this. Very easy to do it. And the important here is this one, RC circuit, another RC circuit. That's it. Okay, that's the important thing. Okay, let me tell you how to do it. Let me draw this signal here. Let's say this is our ST or RT, okay? This is what we transmit and this is what we receive. From here, we want to recover this envelope. And how to do that is this signal now comes into here. You see AM wave. This is where you receive this signal. And now this signal comes in here and goes into here. Since we have a diode, it does not go back, okay? It only goes there. And now here, now we see the capacitor. And what is the what does the capacitor do typically? It accumulates energy. It charges, right? So here, what you do is that you are charging. Okay, you are charging. You have your certain voltage here. Let's say, since you have this signal, you have this voltage or this voltage. So typically, initially you have 0 voltage, and you are getting some signal. So here is a higher voltage. than here, right? So it'll be charged. It'll be charged. Let's take a look at here. Initially, we start from here. The voltage goes up. And while goes up, we have higher voltage here. It goes and it charges. So when the signal goes up, the capacitor here will charge. Okay, it charges. When you go to top, now it starts to go down. And voltage here now goes down. In that case, since this voltage goes down, now we have enough charged here. Now voltage here can be higher than this one because this one goes down and this one is already charged enough. Okay, so when signal goes up, this capacitor will be charged. And when this signal here goes down, this one will be discharged. Why? Because now here has a higher voltage. This one becomes like a battery now, right? This one will be discharged. So right here, it'll discharge. When you discharge, using this resistor, we want to discharge it very slowly. So the idea here is that you want to charge it very fast. When you charge, you're going to use RC circuit, this RC. Okay? Using this RC, when you multiply R and C, now you can calculate some constant, right? Constant. So based on this R and C, you can design that you can charge this one very fast. Charge it very fast and discharge it very slow. In that case, what happens is, when signal goes up, you are charging very fast. And when signal goes down, you start to discharge. You release the energy, but that's going to be very slow. So when you slow discharge, it goes like slow like this. Okay? Your original signal here goes down, but right here, we want to discharge energy here slowly. So it'll slowly discharge. And eventually, the signal is much faster, so it goes down and come back again. Still, it is discharging. And now we'll see here, then again goes back up, charging a little bit, and discharge, and charge a little bit, discharge, charge a little bit, discharge. So charging is very fast, discharge is slow, like that, right? So you see this kind of picture in here. Okay? That's where you measure. This is where you get the output. And the output right here is going to be like a blue. So now when you see this blue, you see that it's not exactly the same, but it's almost like envelope, right? It's almost like envelope. So that's what you see here. Look at this picture. This picture is what I just said. Charging it fast, but discharge slow. Charging fast, discharge slow. Like that, right? So from here, from this fast-moving signal, now you discharge it slow, then you see this kind of signal. Okay? It's not very clean because you discharge a little bit. So it's like a noisy signal, but still, when you look at this shape, it looks like almost as an envelope, right? And how to get this one? Very simple circuit. You cannot design simpler than this one. It's the simplest design because you have only two RC circuits. When you design this, as I said, you need to make sure that charging fast, discharging slow. And how to do that? You need to design the RC value based on this condition. So this is the condition you want to satisfy, especially here, right? RLC, this is a discharging time constant. So when you multiply R and C, that's called time constant. Okay? When you look at this one, RL, that's called the load, RL. RLC, that's this part, this RC. This RC is for discharging. And you want to choose this RC, R times C, and make it discharging constant. And that discharging constant is, you need to make it with this condition. And this part is for charging time constant. You want to make the charging constant to be like that. So the idea is charging it quickly, discharging it slowly. Okay? That way you are discharging it slowly like that. You get this output here. Now after that, what do you need to do? This is like a very unclean, noisy kind of signal. So next thing to do is to do low pass filtering. Once you do low pass filtering, now you do smooth signal. That's it. That's it for receiver. Okay? That's all you do in the envelope detector at the receiver. So that's very simple. But in order to use this simple envelope detector in the receiver, what you need to do is that you need to have DC addition. You need to add the DC. Okay? So that's what it is. This slide shows you the advantage and disadvantage of AM. Okay, and we can talk about this in the next time.